Welcome to Math 31. This is a continuation of lesson 5 on the area problem. So for the previous part, we looked at getting an under approximation using inscribed rectangles, and then we did an over approximation, and then we averaged the two and got an answer for it. And it was a lot of work, even for a simple quadratic. Now we're going to develop a better method that will lead us to a faster and actually a more accurate method as well. And that is using limits. So I'm going to take the same question that we did before, f of x is equal to x squared. Everything is exactly the same. But we're taking we're getting from 0 to 2. It looks like it's a little bit off with those triangles, but it's pretty close at least. So what we do, just to make this whole thing work out, is we divide this into a certain number of equal subintervals. So we divide the interval into n equal subintervals. So we're not assigning a specific amount for them. The 10 that we did before, you may have noticed, we had to average two fairly different numbers because there were big gaps in it. Even just by inspection, we could see we didn't do a good job, or really accurate. So the more you have, the better, the more subintervals. But this is going to mean that if we do that, that we're going to get something like this, where we're going to have the intervals are going to be, because the total distance is 2, then each interval, which will be the width ultimately, is going to be 2, the total, divided by n. So our entire setup is going to be starting at 0. Now I'm going to do these ones, by the way, inscribed. Okay, so I'll take these left corner ones. Now this is not necessary. It really doesn't make any difference which way you do it. So I'm just doing it this because. So if we do it in this form, the first interval is 0 as a lower limit, 2 over n as the upper limit. The next one is going to be 2 over n as the lower limit. Now, if you added on 2 over n, you've got a common denominator, so 2 over n plus 2 over n is 4 over n. And then, do a few more, 4 over n all the way up to 6 over n. And then keep it going. And the very last one will have the upper limit, of course, of 2. But the one you got to be careful with is the one before, and that'll be 2 minus 2 over n. Now, to make that a little bit easier to work with, I'm going to get a common denominator of n. So if you multiplied the 2 by n, you'd get 2n minus 2 over n and then 2. So that'll help us, believe it or not. So those are the intervals that we're contending with, and the width, as was noted before, is always going to be 2 over n. But for the first interval, the length or the height, if you preferred, is as always, or as with the previous example, would be f at 0. So the endpoint is on the left corner, so I'm doing that. Now that means, of course, that we're going to have we won't have n terms. We're going to actually have one less than that. So let's file that away someplace. It's going to matter. The next one, interval, will be 2 over n for a width, and then the length would be f at 2 over n. And then so on like that. The next would be 2 over n, and then f at 4 over n. And then so on. And then the very last one, I'm going to have to sneak this down below, so a little sloppy looking, but the height or the length would be f at 2n minus 2 over n. So I'll get a little more space here to work, and we're going to get the area again, like we did before, just by adding all of these together. And it's a little sloppier because we've got the 2 over n deal. But 2 over n times f at 0 plus 2 over n times f at second interval, which is 2 over n, and so on like that. 2 over n for the width, f at 4 over n, all the way up to the very last one, which would be 2 over n multiplied by f at 2n minus 2 over n. Now, plugging into the formula, and we're going to get the area is equal to 2 over n multiplied by, well, of course, that's times 0, so that one's going to go away, plus 2 over n, so this I'll get rid of it right away, times 2 over n squared, etc. like that, plus 2 over n times 4 over n squared, etc. like this. A lot of rewriting the same thing over and over. Luckily, we don't have to do this much longer. Now, when we simplify this, we should be able to take out a factor of 2 over n, and that makes sense from both of them, or for all of them. So this factor of 2 over n can be taken out, but you can also take out a factor, each one of these, if we expand the denominator and the numerator, like this would be 2 squared over n squared, we can also take out a factor of 1 over n squared. And if we do that, all we're left with then is 2 squared. The numerator is all squared, plus 4 squared, plus 6 squared, etc., all the way to 2n minus 2 squared. So that makes sense. So that's actually 2 over n cubed. So now if we set up as a sigma, we have a fairly easy one to do, because area is going to be equal to the sigma of 2 over n3. There's our common factor, which then will be taken right out of it. And then the formula, if we set it up in the I formula, this is I is 1, this is I is equal to 2. So the formula is actually simpler, because it's just going to be 2 times the I value all squared. And we're taking this from I is equal to 1, but we're not going all the way up to n because we dropped one term. So it's actually going to be n minus 1. There were n originally, but because the first one was 0, we have n minus 1. Now that's going to come into play later on. And simplifying this further by taking out the numbers, the common factors, this is 2 over n cubed that gets taken out. But we also can take out, when we expand 2i squared, that's 4i squared. So we take out a factor of 4, and then we get I squared, which is what we want, because we want it just like I squared. So this is 8 times I squared. Now remember the formula for breaking down something that's in I squared form. So this becomes, and be really careful, because the sigma, I'll take this up here, I squared is equal to n times n minus 1, n plus 1, and then we get 2n plus 1 over 6. So that's where this is going. So we have 8 over n cubed, the common factor, multiplied by n. Now n, in fact, is not n, it's the upper limit. So in this case, the n is going to be n minus 1. So we have to put whatever this upper limit is. So that's n minus 1, so you've got to be real careful. And then n plus 1, n minus 1 plus 1. And then 2n minus 1 is 2 times n minus 1 plus 1. And then all over 6. So this is going to give you the area is then equal to 8 over n cubed times n minus 1 times n. And then if you clean this one up, you'll get 2n. Minus 2 plus 1 is minus 1. And this is all over top of 6. Now we can also simplify this. We can bring this up a little bit because the 8 and the 6 will break down. So we'll get 4 over n, and the n's will cancel as well. One of the n's will. So divide this will give you 4. This will give you 3. Now if you FOIL that all out, you're going to get n minus 1 times 2n minus 1, and then multiply in your factor of 4. We will get, and check this note carefully, but it's pretty straightforward quadratic, 2n squared minus 12n plus 4. So I FOILed those, and then I multiplied out the 4 in, and then the denominator is just going to be the 3, and then the n squared that we've got. And now the idea at this point is we recall that the basic principle is to get the make the n value as large as possible. So the more small intervals you have, the more accurate is your approximation. So we take the limit as n increases without bound. And if we do that to this rational expression using the limit methods that we worked with earlier, we divide every term by the biggest factor of n anywhere, really, denominator or numerator. So you're going to get 8 minus 0 plus 0 all over 3. So we get equal 8 over 3. So this limit, or the limit as n gets smaller and smaller, is 8 divided by 3, which is 2.67. So therefore, the area is equal to 2.67 square units. So we did it by taking limits instead of breaking it down to an arbitrary n value. So it worked. It worked better, actually. Still more work than we want, because we were vulnerable for a few things. Like this worked nicely in a quadratic, because the quadratic did give us the I squared, which gives us a formula. But what happens if it was something other than a quadratic? We're going to have difficulties. So we have to go further with this, but this does give us some information. So I'm going to bring up the next little bit of space here to work on this. But if we were to consider, say, a setup like this. Now this, in this case, you notice the curve is a little bit different. I've inscribed them, but I've got the right upper limit to be touching the curve. It doesn't really make any difference. But let's make a few generalizations with these ones. Now, if we take a look at the size of the interval, we could call that delta x, because that's always going to be the width. So the width will be delta x. And this is for y is equal to f of x. Now, what I want to do is get the actual height, the length of this. And to do that, I need to find out what the values are for each of the the x values along the axis. So I'm going to call this xi. And xi is equal to a, the original, plus I times delta x. So that just means to find out what each of these x coordinates are along the way, you start with a, and you add on however many delta x's you need. So for this first one, I is equal to 1, I is 2, I is 3, etc. And then that would tell us that the length of this, of each rectangle, is going to be equal to the f value for xi. So whatever, like right there, would be f at x1. There would be f at x2, etc. like that. And then what we need to do is add all these areas together. And we can do it because the total area is equal to the limit as n gets bigger and bigger and bigger, and then the sum of all these starting at 1 to however many n's you have. So in this case, it's not a big deal, but you would have either circumscribed or inscribed, so the endpoints, depending on whether you put the endpoint on the left or the right, would determine the exact number of n's you have. But it ultimately doesn't make any difference. As we saw in the previous one, you still have an infinite number of rectangles, whether you go left or right upper limit. And then this is your length, and this is your width. And it's the sum of all these. That's what the sigma does. So you add all of these together. So the sum of all the rectangles. Amazing. And that warrants a little box around it. So this is what they call a Riemann sum. And there's all sorts of examples of these, sometimes using polygons. But the method itself is, the Riemann method is essentially to break it down into these tiny rectangles. And if you want to get the area, you just develop a method algebraically, taking limits, to add them all up. So there has to be a pattern. And the one we looked at is probably the easiest of all. And then we work them out sort of Armstrong like that. So that's it for this lesson. And the next, where we go from here, is working with the fundamental theorem of calculus, which does allow us a better, more reliable way to solve these ones. Thank you for your time.